Hi, my name is Magnar Nordahl. I'm a captain instructor on ATR aircraft. In this video, we will have a look at the flight controls in ATR. They are divided into primary and secondary flight controls. With a few exemptions, they are pretty straightforward. The primary flight controls are elevators, rudder, and ailerons. All of them are manually operated. They can also be operated by the autopilot. Each one of the primary flight controls have electrical trim. The secondary flight controls are spoilers and flaps. They are actuated by hydraulic power. Okay, let's go. Each control column is connected to its associated elevator. From the control columns, there are cables running under the floor to the electric and electronic racks, up to the ceiling, and then aft to the tailcon area. Here, the cables are attached via belt cranks to control rods, which act on the elevators. The captain controls the left-hand channel with the port elevator, and the first officer controls the right-hand channel with the starboard elevator. The elevator channels are connected with a pitch uncoupling mechanism between the elevators. Therefore, when one of the pilots moves the control wheel back or forth, the movement is transferred to the other control column via the elevators. There's a reason for this. If one of the elevator channels is jammed, pilot flying will not be able to move the elevators. The pilot flying will call pull, and both pilots will pull the control column. The uncoupling mechanism will disconnect when a force of 520 Newton, or slightly more than 52 kilograms, is applied. One of the elevators will then be free, and the associated pilot will become pilot flying. When the pitch uncoupling mechanism disconnects, a pitch disconnect alert is triggered. With only one elevator, the pitch control is mushy, so you must fly the airplane gently and not too fast. The speed limitations are given in the QRH. The elevators might disconnect if you use reverse at low speed because turbulent air from the propellers will rock the elevators. There have also been cases where both pilots, in a stressful situation, have applied opposite elevator inputs, causing the uncoupling mechanism to disconnect. This is a CRM issue and can be dangerous. There is only one pilot flying, and if the other pilot wants to take control, he or she must call my control. The pitch uncoupling mechanism can be reset after landing. On early ATR variants, it's done by a mechanic. On later ATR variants, it's done by pressing the elevator clutch push button on the right-hand maintenance panel. The procedure is in the QRH. A stick shaker is attached to the base of each control column. A stick pusher is attached to the captain's elevator channel. The stick pusher and shaker system can be disengaged with this push button. The autopilot pitch actuator is attached to the first officer's elevator channel via a belt crank. In addition, the autopilot also acts on a pitch trim. Each elevator has a trim tab operated with electric actuators. The actuators are synchronized with a flexible shaft. If this synchronization fails, a pitch trim asymmetric alert is triggered. Pitch trim is operated with two rocker switches on the control column, and both of them must be pressed in the same direction to operate the trim. Full trim travel takes 30 seconds. An oral wooler sounds when the pitch trim runs for more than 1 second. The pitch trim does not have a mechanical backup. Instead, there is an electrical standby trim with a fully independent electrical circuit connected to the pitch trim actuator. The standby pitch trim switch is located on a pedestal. Manual activation of the pitch trim will disengage the autopilot. The trim indicators are located on the center instrument panel in the airfield cockpit and on the engine warning display in a glass cockpit. The pitch trim indicator shows the position of the starboard pitch trim actuator. The green band indicates allow pitch trim setting for takeoff. Note, ATR 42 and 72 have different scale on the indicator. The rudder is controlled with the rudder pedals. The pedals are interconnected and there is one pair of cables to the tail section, where the cables are attached to the respective bell cranks. From there, the movement is transferred to the rudder with a control rod. A third bell crank is attached to the autopilot yaw actuator. A rudder damper prevents damage to the rudder in case of gusty winds when the aircraft is on the ground. It also prevents snappy movements of the rudder on ground and in flight. The rudder has a spring tab, which is very different from the trim tab used on elevators. A trim tab is adjusted by the pilot or the autopilot and creates an aerodynamic force that holds the elevator in a certain position. The rudder pedals are attached to the rudder and the spring tab. This is a bit complicated, but I hope I got it right. When you apply maximum rudder at zero airspeed, the rudder will move to full deflection. Then the spring tab will move. This is what you see on this video. Notice the spring tab is moving when the rudder is at full deflection. The rudder force can be very heavy at low speed on the ground when you have crosswind. When the airspeed increases, the aerodynamic force on the rudder will start to resist movement of the rudder. So when you press on the rudder pedal, the spring is compressed. The compression of the spring increases with the airspeed. At the same time, the rudder pedal will act more and more on the spring tab itself. In other words, when the airspeed increases, the rudder pedals start to act more and more on the spring tab and less on the rudder itself. As a result, the force needed to hold the rudder at a certain position is nearly constant at all airspeeds. And this is important when an engine fails. Without the spring tab, the pilot will not have enough strength to hold the rudder at full deflection. Rudder trim is performed by offsetting the spring tab's zero position. The actuator is operated with two switches, one above the other. Both of them must be pushed in the same direction to operate the trim. Full trim travel takes about 15 seconds. The rudder trim indicator doesn't show the position of the tab, because its position depends on the airspeed. Instead, the rudder trim indicator shows how much the trim actuator is moved from its neutral position. At takeoff and landing, the rudder trim is neutral. In flight, the rudder must be trimmed to the right to ensure coordinated flight. The amount of trim increases with the speed. On variants with AFIS cockpit, the rudder trim is operated manually. On variants with glass cockpit, the rudder trim can be operated manually when the yaw damper is off. The trim indicator is then blue. When the yaw damper is on, the rudder trim is automatic and the trim indicator is green. Manual operation of the trim is then inhibited. The trim indicator turns amber in case of rudder mistrim message on the FMA or yaw auto trim fail message on the FMS. In those cases, a blue arrow will appear. You can then trim the rudder in the direction of the arrow. This is the Releasable Centering Unit, RCU, also referred to as the rudder cam in the before takeoff checklist. It stabilizes the position of the rudder pedals. The RCU is like a toothed wheel with a pin inserted and hold the pedals in place. Every time you use the rudder trim, the RCU disengages. When you release the rudder trim switches, the RCU engages again, maybe in a new position. To be specific, the RCU disengages when you push the upper rudder trim switch to the left or the lower rudder trim switch to the right. Before takeoff, The captain will center the rudder pedals and then flip the upper rudder trim switch to the left. Very often you can feel the rudder pedals make a jolt like this. All ATR variants, except for the 42-300 and 320, have a rudder travel limit unit, TLU. The TLU is automatic and prevents excessive rudder deflection at high speeds. At takeoff, the TLU is in low speed mode, allowing for full rudder deflection. When accelerating 385 knots, the TLU changes to high speed mode, restricting the movement of the rudder. When decelerating 380 knots, the TLU changes back to low speed mode, and in case of a system failure, the TLU can be operated manually with this switch. The drawing in the FCOM is misleading, as it appears that the rudder might be left with full deflection if high speed mode is engaged with full rudder deflection. Thankfully, this is not the case. At low speed, the TLU is open like this and allows for full rudder deflection. At high speed, it closes like this, restricting the movement of the rudder. This is the full movement of the rudder in low speed. And this is the full moment at high speed. As you can see, it's very small. If the TLU is in high speed mode at landing and you are not aware of it, you will have the impression that the rudder cannot be moved. Therefore, checking the TLU is part of the before landing checklist. The ailerons are controlled with the control wheels. The control wheels are interconnected, and there is one pair of cables to the center section of the wing, where the cables are attached to the respective belt cranks. From there, the movement is transferred with control rods along the wing trailing edge to the ailerons. A third belt crank in the wing center section is attached to the autopilot roll actuator. In the wing center section, there is also a position transmitter, which gives the position of the ailerons to the FDAU, which feeds the flight data recorder. On early ATR variants, including the first 500s, the ailerons have balance tabs. The balance tabs is connected to the aileron and moves in the opposite direction of the aileron. This creates an aerodynamic force that assists in moving the aileron. However, the control force increases with the airspeed. At the end of the 1990s, ATR changes to spring tabs. The benefit with spring tabs is that the control forces at high speeds remain pretty much the same as for low speeds. At the same time, the control wheel travel increased from 65 degrees to 87 degrees left and right, and position transmitters were added to each aileron. However, the aileron travel remained the same, 14 degrees up and down. Roll trim is performed by changing the neutral position of the left-hand aileron tab. The right-hand tab is not trimmed. Full trim travel takes about 30 seconds. The roll trim is operated with a double rocker switch on the pedestal. The aileron trim cannot be operated when the autopilot is engaged, unless you receive a retrim or mistrim message. The spoilers have one purpose, and that is to assist the up aileron by adding drag. The spoiler deploys when the associated aileron deflects more than 2.5 degrees up. This reduces sturge roll in flight and is important for passenger comfort. The spoiler is also important when departing and landing in crosswind. Without the spoilers, maximum crosswind component at takeoff and landing is reduced to 20 knots. The spoilers are operated automatically and actuated with hydraulic power. Only one spoiler can be activated at a time. An indicator in the overhead panel is illuminated when the associated spoiler is not retracted. This indicator is blue on aircraft with EFIS cockpit and green on aircraft with glass cockpit. According to ATR philosophy, blue means manual operation, which is true when it comes to the ailerons. But the spoilers are operated automatically as a response to the position of the ailerons, Therefore, green is the correct color. I want to say some words regarding the use of ailerons during takeoff and landing in Crosswind. The ATR has a high aspect wing mounted high up. This, together with a narrow landing gear, means that the aircraft is sensitive to crosswind. It is imperative for directional control that the wings are kept level in crosswind at takeoff and landing. If the crosswind component is 7 knots or more, and you don't use the ailerons correctly, your directional control might be compromised. The amount of aileron deflection depends on the crosswind component and the speed of the aircraft. And remember, the spoiler creates drag and with it a yawing moment. If you for any reason use the control wheel like you steer a car and you apply left and right aileron, the yawing moment will change, making directional control much harder. Sometimes I see pilots are clever to hold the ailerons into the wind at takeoff, but they forget to do the same at landing. And here is a little secret. The runway slopes to the sides for water drainage. Look at this picture. It's taken from the cockpit of an ATR, about 2.5 meters above the ground. We can see the zebra stripes on the nearest half of the runway, but we cannot see the zebra stripes on the other half of the runway. If you are not on the center line, it will be very hard for you to keep the wings level. Imagine you are on the downwind side of the runway. Then the upwind wing will point up and the wind will try to lift it further up. Even maximum aileron may not help, and the drag from the spoiler will make it harder to maintain directional control. But you can use this knowledge to your benefit. When you have a strong crosswind, you put your nose wheel 1 meter to the upwind side of the center line, and the wing will already have a slight bank into the wind. This will require less aileron, which reduces the deflection of the spoiler, which makes it easier to maintain directional control. Each wing has 2 flaps, inboard and outboard. They are mechanically linked together. Each flap has a hydraulic actuator. The actuators are fed by a flap valve block, which is electronically controlled by the multifunction computer MFC. ATR 42-300 and 320 don't have MFC, so instead I had a flap position unit. To select a flap position, the lever must be lifted first, and then moved to a notch. It is not possible to set intermediate flap positions. ATR 42-300 and 320 have the following flap positions: 0, 15, 30 and 45. The last position is guarded and must only be used for emergency landing in normal conditions. The reason is that flight tests with artificial ice shapes revealed that the horizontal stabilizer was prone to tailplane stall with flap 35. Later ATR 42 variants have flap 0, 15, 25 and 35. All ATR 72 variants have flaps 0, 15 and 30. On the 42-300 and 320, the flaps indicator shows the position of the interconnection torque shaft between the left and right flaps. On all other ATR variants with AFIS cockpit, the flaps indicator shows the position of the right-hand flaps. A blue extension flag indicates that the flap valve block is commanding flaps extension. If the flag doesn't go away, then there is a hydraulic leak in the flap system. On ATR variants with the glass cockpit, the flaps indicator shows the average position of the left and right flaps. White color indicates 0 flaps. Cyan or light blue indicates the flaps is extending or retracting. If the cyan color doesn't go away, then there is a hydraulic leak in the system. Green color indicates that the flaps is in the commanded position, plus minus 1 degree. Amber is associated with one of the following conditions. 1. Flaps asymmetry. On ATR variants with MFC, the MFC records the position of the left and right flaps. If the difference between them exceeds 6.7 degrees, a flap asymmetric caution is triggered. On variants with EFIS cockpit, there is an amber alert light on the central instrument panel. ATR 42, 300 and 320 do not have MFC and flaps asymmetric caution. Visual indications are uncommanded roll tendency and a frozen flap indicator. 2. Flaps jam. The flaps doesn't move. Variants with EFIS cockpit do not have any other alert than the flaps is not moving. 3. The flaps is not in correct position for takeoff when applying power or pressing the takeoff config test push button. 4. The position of both flaps is invalid. Red is associated with an uncommanded flaps retraction. When the flaps has moved 3 or 4 degrees, depending on ATR variant, the master warning is triggered with a flap unlock message. This can be a serious situation during takeoff or final approach because the stall speed will increase rapidly. Finally, there are flaps indicators on the outer flap hinge fairings, and they are visible from the cockpit. The Gust lock protects the elevators and ailerons when the aircraft is on the ground. To engage the Gust lock, move the lever to the full aft position and push it down. Pull the control column aft until the elevator is locked in place. Then move the control wheel left and right until the ailerons lock into place. The elevator lock is mechanical and locks the control column in pitch. On ATR variants with ailerons with balance tabs, the aileron lock is fully mechanical and locks the control wheel in roll. On variants with ailerons with spring tab, the aileron lock is electromechanical and controlled by the MFC. There are 2 microswitches in the Gust lock lever, and they are connected to the MFC, which control locking devices in the ailerons. An amber aileron lock caution is triggered when there is a disagreement between the Gust lock lever and one of the aileron locking actuators. A config warning is triggered when the aileron locking actuators are not fully retracted and the power levers are set for takeoff, or when there is a disagreement between the aileron locking actuators and the Gust lock control during a takeoff config test. And as a bonus, I will show the interior of the tail cone. That's all for this time. I hope you liked the video. Please support my channel by sharing with your friends and all that stuff. Thank you for watching. Have a wonderful day and happy landing!